All right, let's dive in. If you've ever found yourself prepping for a coding interview, or maybe just trying to speed up some code you've written, you have definitely run into the big sorting question. So today, we're going to demystify the whole thing and give you a super practical guide to picking the perfect sorting algorithm for pretty much any situation. And this is it, isn't it? The classic question. It's the one that gets asked in every computer science class, every technical interview. You've got all these options: quick sort, merge sort, heap sort, the list goes on. So which one is the one, the best? And there it is, the simple, kind of frustrating, but 100% correct answer. It depends. But on what? That's the real question, and that's exactly what we're going to break down today. So why does this matter so much? I mean, why is this such a fundamental question? Well, because sorting is one of the absolute building blocks of computer science. It's everywhere, from you searching for a file on your computer to an application scheduling tasks, all the way to how graphics get rendered on your screen. Getting sorting right means your code is fast and efficient. Getting it wrong, well, that means you're in for a slow, clunky experience. At its core, sorting is just about creating order out of chaos. And for most of what we're talking about here, we'll be in what's called the comparison model. Now, that sounds fancy, but it just means the only tool we have in our toolbox is asking a really simple question over and over. Is this item less than or equal to that item? That's it. Now, here's where it gets really fascinating. For this kind of sorting, this comparison-based sorting, there's a mathematical speed limit. Seriously, you can only go so fast. You can think of it like the sound barrier, but for algorithms. And here it is, omega of n log n. Now, in all that complexity notation, omega basically means the best possible worst-case performance you can ever hope to get. It's the floor. You might see theta for an average case or big O for an upper bound, but for right now, just think of n log n as that fundamental speed limit. It's the gold standard we're all trying to hit. So where in the world does this speed limit come from? Well, imagine you have a list of n items. There are n factorial, which is a ridiculously huge number of ways they could be jumbled up. Every single comparison you make, every time you ask, is A bigger than B? You're basically cutting the number of remaining possibilities in half. It's like you're navigating a giant branching tree. And the math just shows that to find that one single correct path to a sorted list, you're going to need at least n log n of those questions in the worst-case scenario. Okay, so if we can't actually break the speed limit, how do we get as close as we possibly can? Well, let's meet the main contenders. And to make this super clear, we're going to use a simple analogy for all of them. Imagine you're just sorting a pile of books on a shelf based on the number on their spine. First up, we've got insertion sort. Honestly, this is the one you'd probably come up with on your own. It's simple, it's super intuitive, and it's a fantastic place for us to start. This quote just nails it. You pick up one book from your unsorted pile, look at the books already on the shelf, and just slide it left until you find its correct spot. And here's its superpower. If your shelf is already kind of sorted, just a little messy, then tidying it up this way is incredibly fast. All right, next, let's look at a totally different, much more powerful idea with merge sort. This one is an absolute titan of sorting, and its whole strategy is divide and conquer. It doesn't even try to sort the whole shelf at once. And this is the real magic of merge sort. It breaks the big, scary problem down into the simplest possible problem, a single book. I mean, a single book is already sorted, right? Then it just methodically merges these little sorted stacks back together, like perfectly shuffling two decks of cards until the entire shelf is in perfect order. It's systematic, it's predictable. And now for the algorithm that, let's be honest, usually lives up to its name, quicksort. It also uses that divide and conquer idea, but in a completely different way. It doesn't just blindly split the list in half. Quicksort's entire strategy hangs on this idea of picking a good pivot. You just grab one book, call it the pivot, and then everything else just gets shuffled around it. All the books with a smaller number go to the left, all the ones with a bigger number go to the right. Then you just do the exact same thing to those two new, smaller piles. The whole game is just picking a pivot that splits the pile nice and evenly. So we've got these different strategies, right? Inserting one by one, splitting and merging, or pivoting and partitioning. How in the world do we decide which one to actually use? Well, it all comes down to a few really critical trade-offs. These are the three lenses we've got to look through. First, time. Pretty simple. How fast is it? Second, space. How much extra RAM does it need to do its job? And third, this one's a little more subtle but super important, stability. So imagine you have two books with the same number, say 5, but one is red and one is blue.
A stable sort guarantees that if the red 5 came before the blue 5 in the original messy pile, it will still be before it in the final sorted list. That can be a huge deal. So let's put the two heavyweights, quicksort and merge sort, right up against each other. Quicksort is, on average, usually faster in practice and uses very little extra memory. It sorts in place. But merge sort gives you this rock-solid, predictable, guaranteed performance every single time. And it's stable. It's that classic trade-off. Do you want blazing practical speed, or do you need guaranteed performance and stability? This table really lays it all out at a glance. You can see right there, Quicksort's average time is fantastic, n log n. But look at its worst time, n squared. That's a huge difference. That's the risk you run. Compare that to merge sort, n log n, every single time, but it costs you extra memory. Now look at heap sort. It hits that n log n sweet spot even in the worst case, and uses almost no extra space, which makes it super reliable. And then you've got this outlier counting sort, which looks like it's breaking our speed limit. And it kinda is, but it's a specialist. It only works if you're sorting integers within a specific limited range. Okay, so here's the real takeaway. The crucial point is knowing which algorithm to pull out of your toolbox and when. It's not about memorizing a bunch of formulas. It's about having a mental playbook for whatever situation you're facing. And this is that playbook. It's a decision tree. Is your array tiny, or maybe it's already almost sorted? Don't overthink it. Insertion sort will be lightning fast. Do you absolutely need stability? Maybe you're sorting data by multiple columns. Merge sort is your reliable workhorse. What if you're in a situation where you need that worst-case guarantee, but you have no extra memory to spare, like on an embedded system? That is a job for heap sort. Want a fast, general-purpose sort that's usually the best bet? Randomized quicksort is your go-to. And finally, if you know for a fact you're just sorting integers in a pretty small range, nothing can touch the speed of counting sort.
Now, here's the thing. In the real world, you actually don't have to just pick one. The standard sort function that's built right into a language like Python is called timsort, and it's a super clever hybrid. It actually scans your data, finds small chunks that are already sorted, and uses insertion sort on them. Then it uses merge sort to combine all those chunks. It's adaptive. It actually exploits any order that's already in your data to run way faster.
And, ultimately, the fact that these amazing hybrid sorts, like timsort, even exist, it reveals a deeper truth. The most powerful solutions are the ones that adapt. So the real question isn't just which algorithm is the best. It's a much more interesting question. What does my data actually look like? What are its hidden patterns? And how can I best exploit them? Thanks for watching.